Hi, everyone. This is Kevin Limtow here to describe my Project 8 report, wherein we are creating a combination of hardware and software to capture yaw, pitch, and roll data. That's going to be using a BNO055 IMU, which is kindly provided by our professor. So that IMU is going to be connected to, in my case, an Arduino Uno, but it could really be any Arduino that can read out data from that IMU using its built-in I2C interface. From there, the Arduino is going to transfer the IMU data, specifically the yaw, pitch, and roll data, to a Raspberry Pi using a serial interface, just USB serial. The Raspberry Pi will stream that via Wi-Fi to a host PC for display. So I'll describe some of the requirements, the design of the system that I built, and the implementation details for that build before getting into the live demos. So first and foremost, some of the requirements from the course materials. We need to mount an Arduino to the quadcopter that we built way back in Project 4. We got to connect that BNO055 IMU to the Arduino. We got to capture yaw, pitch, and roll data. We need to send that IMU data to the RPI, stream that IMU data from the RPI to a host PC, and then display everything. And one key requirement in this particular project is to leverage the free RTOS real-time operating system that can operate on Arduinos. And so that's what I've gone ahead and done, and I'll describe in a little bit more detail once we get to the design and implementation point of this video. From there, I do have a few requirements that actually mostly stay the same from Project 7. We're still going to be using the Raspberry Pi, so all the necessary tools still persist. We're using a wireless access point, which is managed by this RASP app, free-to-use software program. Also, just because it's convenient and cool to see, I am still live streaming video from a web camera, and that'll be part of the live demonstration as well. And that is managed by the software application called Motion. Moving into the newer things for this particular project, we're adding in application embedded software that needs to run on an Arduino microcontroller. We're adding in the inertial measurement unit. Those are two elements that are really brand new to this particular project, and they're going to be integrated together with components that we've built up along the way in projects 6 and 7. In my case, I'm going to be using an Arduino Uno because it's what I've had over the course so far, writing it in C or C++. And really, the key to all this is I'm going to be periodically collecting and transmitting IMU data at a pretty high frequency, 10 hertz. Any faster, and it's just zooming by the screen. Any slower, and we could go slower, but it's nice to see the real kind of live feedback as I move the quadcopter around, and 10 hertz seems like it's a sufficient frequency for that. The transmitted data, I'm going to be sending yaw, roll, and pitch data in that order, all in degrees, with a couple decimal points of precision there. And just because it's valuable to have to ensure that the data coming from the IMU actually makes some kind of sense, I'm also sending the calibration status of the larger IMU system, the gyroscope, the accelerometer, and the magnetometer over serial as well, so I kind of know where the sensor is in terms of its calibration routine. Moving on into the design. The design mostly stems from previous Project 6 and 7 designs in terms of hardware design. Really what I'm adding is the Arduino Uno and the BNO055 IMU that I actually put on a small little breadboard that came in one of my kits, the Arduino kits. So that's a nice little package, and it actually, I couldn't find a good representation, but it goes on a little breadboard, protoboard shield that goes on the Arduino, and I'll have some pictures of that later on. In terms of off-the-shelf software, I do still have plenty of that. I'm using the Raspberry Pi OS, the Motion software program that I mentioned above, and RASP app I'm using as a wireless access point. But more specifically into what's new for this project, on the Arduino embedded software, I am running free RTOS just so we can gain more experience with an RTOS. And specifically, there are two tasks that I am creating and using over the course of this particular application embedded software. The first task is the most important one, which is to read the IMU. And so I've given a task name, which is human readable. The stack size is 128, which is one of the default ones that actually comes with some of the example code that you can get from the free RTOS library. I was very, very glad they provided that. The first thing that the task does is it instantiates an IMU sensor event. It gets that sensor event. Then from there, it can print yaw, pitch, and roll data, which is actually really cool. I'll talk about that in a little bit. It can also get calibration status and print that calibration status. And what we've learned in using free RTOS is that you're not just going to use the delay command. There is an actual task delay function that delays by a number of cycles. I'll describe that in a little bit as well. The second task is just, signs of life from the Arduino. It's nice to have. So we can just kind of visualize that it's doing something. So it's going to initialize the built-in LED pin, brings that pin high, uses a task delay again for about a second, brings the pin low, and then there's another task delay for a second. So these two tasks are handled completely by the free RTOS task scheduler. And based on their priorities, you can see here that the IMU read is given a higher priority than the blink task. For logical reason, I care much more about the IMU data than I care about blinking an LED. But these are the two tasks that I've instantiated in my code. And the cool thing about the IMU sensor and the library that you can actually get, it's the BNO055 library, the Adafruit BNO055 library, is that it gives you a bunch of really cool tools. So I don't actually have to go about the process of calculating yaw, pitch, and roll data from raw accelerometer and gyroscope data. That would be a whole ton more math than I necessarily remember how to do. So the nice thing is that you can actually get absolute orientation data, which is actually fusion sensor data, as I'm learning from IMUs. It combines, the reason it's called fusion sensor data is because it combines accelerometer and gyroscope values in order to calculate yaw, pitch, and roll. And so that becomes quite easy to report and print over the serial interface. All right, and then I promised I'd get into some pictures of my implementation here. So I still have the Raspberry Pi 4 inside of its case at the bottom of the quadcopter, mounted with double stick tape. The web camera is still there. I've just started to run out of space on this quadcopter to mount all these various components. The GPS module is still on the left-hand side here. Got a battery pack. I've got the mini PIX controller and the GPS module that comes with it, the button, the transmitter. All these sorts of things are really starting to stack up, including, of course, the battery for the quadcopter. So I've stacked the Arduino Uno on top of the mini PIX GPS module. And then on top of that, I've stuck a proto board, a shield, and a breadboard that came with double stick tape. And then I've mounted the IMU on that breadboard, and you can see some of the wires here, which I did make sure were clear of the spinning propeller blades. A few different images there, everything kind of, just haphazardly still hooked together, but it works just fine. And I did clean this up a little bit more after I took this photo with just some extra zip ties to get the cables out of the way. And rather than go through all the code here, I'll jump into Visual Studio Code and show what my main file looks like. I'm including free RTOS in order to use the I2C communication interface. I gotta include wire.h. The Adafruit BNO055 can be talked to using the Adafruit sensor library, and more specifically the BNO055 package. So that's all really nice to have. And then there's also a utility that you can use to do a bunch of math that I wouldn't want to do by hand. or at least in the code. So these are all libraries that I found to be very, very helpful. And I actually pulled a lot of this code from example code, both for FreeRTOS and for the BNO055 Adafruit package. And you can find both of those in the libraries that are provided. So for example, the BNO055 library has the example code that I really use, sensor API, which you see all these included packages. And similarly for FreeRTOS, there you go, by Richard Berry. He provides some very simple programs like this blink analog read, which I ended up using and modifying. Instead of, you know, 2 tasks of blink and an analog read, I made it a task blink and a task IMU read. So a lot of my code that I've shared in the Word document report is actually borrowed heavily from these example codes. And so, as I mentioned, 2 tasks here and a function for grabbing calibration status. The key thing that I found in FreeRTOS is that everything happens in really the setup structure, which is a little bit different. But we're going to begin serial communication, begin using the BNO sensor. This is something that I've found in pretty much every guidance on how to use the BNO055s. They all say to use the external crystal. So I just kept that in place. I don't totally know how useful it is relative to you know, non-useful, but keeping it true, I get reasonably good values from the IMU. I create my 2 tasks, which I described the stack size and priority of in a previous part of this video. And then here are the 2 tasks in definition. Once again, I'm using events, which can be really useful for getting fusion IMU data, which just gives us orientation, which corresponds to yaw pitch and roll values. And then I can also display calibration status as well, which uses the BNO.getCalibration function. The get calibration function. So that's basically it. That is what my code does, and I'll go ahead and cut the video here and jump into first the demo of how this code works, with me just kind of manually moving the quadcopter around, and then I'll actually get into a live flight demo. So thanks so much for listening, and I will move on into the demo. Hi, and welcome back. So now I'll be discussing what my quadcopter looks like when it is all hooked up and connected. You can see on this side the red LED showing the Raspberry Pi enabled and active. It's not showing the green LED because there's really not much going on the system right now. There are a couple LEDs that you might be able to see on the Arduino right up here. And you'll notice that this is just kind of a mess of wiring and cabling. I debated trying to do some more better wire routing of components. But for now, just for test purposes, I think that's good enough. So I have, as once again, I'll bring this into view, the Arduino and the IMU BNO055 on the top of the instrument there. And you'll see that if I can point this or angle it in quite the right way, the forward facing, the IMU is forward facing in the same direction as this mini-pix controller. So everything should notionally be aligned. There's probably maybe like a degree or 2 of just assembly error on my side, but for the most part, pointing straight forward. And everything is powered on. So what I can do now is actually share my screen. And I'll bring us into the Raspberry Pi desktop here. This is just VNC, and I'm currently VNC'd in, so I can access everything. So what I can do is I can go ahead and maybe launch the webcam, perhaps for starters. And I can do that just by saying sudo service motion restart and sudo motion. And that goes ahead and starts the camera streaming process. And so I can open up a browser. And actually, a slight tidbit here, I noticed that Chromium on Raspberry Pi 4 OS 64-bit is painfully slow. It actually just kind of pulls everything down. So now what you can hopefully see here is the webcam stream. Let me scale this over here. And you can see just a tissue box there. But as I move this around, the webcam will face the screen. And I'm getting live webcam footage as I move the quadcopter around and kind of move it. Perfect. So I'm going to place this back down. And in parallel, I have my Arduino code, which I reviewed. It is going to stream out data, serial port data. So I'm going to go ahead and, nope. There you go. Restart this. Open that. Oops, that is actually the wrong port. Let me go ahead and correct that. I have the GPS still connected to the device, so I'm going to go ahead and use a different port. It's actually likely ACM1 now. It just depends on what component connects first to the system. And there we go. So the yaw, pitch, and roll measurements are being streamed over USB or serial to the Raspberry Pi, and it's just constantly streaming at a 10 hertz rate, so it's actually moving quite fast. It is uncalibrated right now. You'll see this system calibration is 0. The gyro, I just left it going, so it is fully calibrated. The magnetometer and accelerometer are not calibrated, but I can go ahead and do that. And in the meanwhile, you'll see as I'm calibrating this, the webcam stream is going to fly around a little bit. So I'm going to try to calibrate just by throwing this around the magnetometer, and I have the magnetometer now calibrated. And actually, I'm not going to calibrate the accelerometer because it's a little more tricky to calibrate. I'm just going to go ahead and leave it here, but demonstrate what the yaw, pitch, and roll measurements look like as I sit here. So I'm going to go ahead and look at those numbers. Yaw is at 93 degrees-ish. If I rotate it and yaw this direction, I see the yaw increases, and if I rotate it in this direction, you'll see that the yaw decreases. And my VNC connection might be a little bit slow. There you go, it has updated. Yaw has decreased there. I apologize, the VNC connection is just a little bit spotty. So I can rotate the instrument, or yaw, change the yaw of the quadcopter, and the yaw changes accordingly. I can now change the pitch, so I'll increase pitch and go up, and the pitch goes up. And when I go down, the pitch goes down. And once again, I'm gonna go a little bit stationary, and then the roll is, right about flat. I can roll this direction and look at the roll increase, and then I can roll to the right-hand side and watch the roll decrease. And so that is yaw, pitch, and roll all on the quadcopter, fully disconnected, well, from the outside world. It is connected to my laptop via a wireless access point, which is slow, but I can get everything streaming over. So I'm going to go ahead and close this up here. I'm going to close that session. Looks like my wireless might be slow here. I'm going to go ahead and close this as well. And that pretty much finishes the demonstration. So that is a yaw, pitch, and roll on the quadcopter. And now I'm going to cut here and we'll go into a live flight. Thanks much.
Starting the recording. Test flight complete.
All right, test flight number 2. Test flight complete.